Hey, Mr. Martin with a quick video over arc length. You will need a calculator, so grab one. Arc length is based upon using the distance formula. We're not going to talk about the derivation of the formula. Rather, we're just going to work some examples that use this formula. So let's just talk about the two formulas we have. So if we have a function that is easier to express in terms of x, we're going to use the first integral where we have s equals the integral from point A to B of the square root of 1 plus the derivative of whatever function squared dx. And if that function is easier to express in terms of y, it's going to be the same integral except we have the derivative in terms of y squared. All of the examples that we do in the notes are going to be based upon x being the independent variable because that's most likely what you'll see on assessments and the AP exam. So most of these integrals are not worked by hand because they produce rather difficult integrals that we can't solve by hand. So we're just going to set up the integral and then use the calculator to do most of the work. Some of them can be worked by hand, and we'll talk about the ones that can be worked by hand. So for the first example, we have y equals 2/3 x to the 3/2. To do arc length, you always need the derivative. So first, the derivative is 3/2 times 2/3 x to the positive 1/2. Multiply the exponent to the front, subtract 1. So this simplifies to just be x to the positive 1/2. So when we set up arc length, we'll have s equals the integral from 0 to 9 of the square root of 1 plus, this is the square root of x, so the square root of x squared dx, which as a rewrite is the integral from 0 to 9 of just the square root of 1 plus x. So this is an integral that we can solve by hand. Let's put this in the calculator now so we know what the answer should be. So we'll clear this out. So math 9 pulls up our integral, and so we're going from 0 to 9 of the square root of 1 plus x dx. And that turns out to be 20.42. So we know this result should equal about 20.42. Now, if we did a u substitution on this, we could have u equals 1 plus x, du equals dx. Our x limits are from 0 to 9, and the u limits are then from 1 to 10. So again, we get our u limits from substituting these x's into this expression. So 0 plus 1 is 1, 9 plus 1 is 10. And so as a rewrite for our integral, we get s equals the integral from 1 to 10 of just u to the 1/2 du, which if we integrate, we get 2/3 u to the 3/2 evaluated from 1 to 10. And if we did this by hand, we get, I would factor out the 2/3. So we have 2/3 times the square root of 10 cubed minus, if we substitute in 1, we'll just get 1. So we check this on the calculator. So alpha y equals pulls up a fraction. So we have 2/3 times the square root of 10 cubed minus 1, and it's still 20.42. So even if we did it by hand, this is one that could be done by hand, we get 20.42. All right, so let's go back for a moment. So here, basically, we're generally going to stop here once we have the integral simplified and set up and let the calculator do the rest of the work. What's most important is that you can calculate the derivative of the function. So for example, 2, we have y equals the ln of cosine x, and we're doing this on the interval 0 to pi over 4. So we still need the derivative, so y prime is going to be the derivative of cosine, which is negative sine x over cosine itself. So negative sine over cosine is going to be negative tangent x, and where we're gonna put this? So we'll say like s equals the integral from 0 to pi over 4 of the square root of 1 plus negative tangent x squared dx. So this is really just 1 plus, so we can just write beneath this. This is just 1 plus tangent squared x. It's still under square root, so we'll just put a square root 2. So we know 1 plus tangent squared is secant squared. So this equals the integral from 0 to pi over 4. If under here we have the square root of secant squared, that's just secant x dx. Now, we don't have a rule for integrating secant, not yet. And we generally just won't. It's worth remembering this. Put a star here. The antiderivative of secant x dx is the natural logarithm of secant x plus tangent x dx. That's it. So in this case, we're going to get the ln of secant x plus tangent x evaluated from 0 to pi over 4. Now, we'll still let the calculator do the work here. So we're going to do math 9, and we're going from 0 to pi over 4. And since the TI doesn't have a secant, we're just going to do 1 over cosine instead. So 1 over cosine x. And now's a good time to tell you to make sure your calculator is in radians. You should get 0.8813. So this integral equals 0.8, how you spell 8? 0.8814, I'm sorry, not 13, 14. Let's go back, and we could also just do that from here. So if we have this same integral from 0 to pi over 4, now the important thing is to remember that we need to include the square root. So the square root of 1 plus tangent squared is just going to be tangent x times tangent x. So we don't have to worry about the whole square thing. And we still get 0.8814. So either way, again, the work is setting up this integral. And we'll let the calculator do the heavy lifting. If you see this on AP exam, unless it's a very simple integral like example 1, you will be required to set up the integral and then use the calculator to get your actual value. And so then for the last example, we have the ln of e to the x plus 1 over e to the x minus 1. So I chose these last two examples so we can remember properties of logarithms. So remember, if we divide a logarithm, inside of a logarithm, we can separate this to be, as a rewrite, the ln of e to the x plus 1 minus the ln of e to the x minus 1. And so when we get the derivative, that's going to be derivative over original, so e to the x over e to the x plus 1 minus e to the x over e to the x minus 1. So that's our derivative. Now, it seems like it's not, you know what? We can just go from here. So we could simplify this and get, I think it would be 2e to the negative 2e to the x over e to the 2x minus 1. But instead, since the calculator is going to do all of the work, we can just set up our integral. So we have s equals the integral from the ln of 2 to the ln of 3 of the square root of 1 plus, and since this is our derivative, we're just going to have e to the x over e to the x plus 1 minus e to the x over e to the x minus 1, all of that squared. Now again, let's go to the bottom for a moment. If we get a common denominator, e to the x times e to the x minus 1 is going to be e to the 2x minus e to the x. And then the same thing here, e to the x times e to the x plus 1 is going to be minus e to the 2x minus e to the x, and then we multiply these two together, so we get e to the 2x just minus 1, and these cancel out. So we get negative 2, not these two cancel out, these two cancel out. This guy is still here, so minus e to the x is still here. So negative e to the x minus e to the x is negative 2e to the x over e to the 2x minus 1. We could put that here, but again, the calculator does the work, so this doesn't need to be fully simplified. Unless I, request that we do. So anyway, our integral math 9 from the ln of 2 to the ln of 3 of the square root of 1 plus, and it's gonna be important that we pay attention to what we're putting in. So alpha y equals, we're gonna have, where's e to the whatever? Where's e? So e to the x over e to the x plus 1 minus where's the e again? E to the x over e to the x minus 1 close parentheses squared. So that's a lot, and it's gonna take the calculator a bit to like do the calculation, maybe. So let's see. 0.5754. So this arc length equals 0.5754. We could check that with the simplified version, but we are not. So again, this concludes this video over arc length. The basic part is that we have to be able to do derivatives. So even when we're integrating, being able to do a derivative is still important. And the rules for derivatives, chain rule, if we wanted to for this one, we could have done the quotient rule. All those things still apply. Thanks.